Um, Hello, everyone. This is a joint work with Chaitanya Agarwal, Eric Koskinen, and Thomas Wies. In this work, we studied the problem of verifying that program traces satisfy a safety temporal property. This problem arises in applications such as input-output behavior, resource access analysis, and others. And the challenge is, can we do better at automatically verifying these properties? In this case, program traces are sequences of observable events. I'll explain that in the next slide. Let's consider this example that models an auction process. It has three parts: bid, close, and refund, and it's a higher order. The program execution starts with calling bid. On the right side, I will show the events generating during the execution of this program. Bid places a non-deterministic number of increasing bids, and for each bid, it emits event 1, corresponding to a bid event, and it also constructs a delay computation corresponding to refunding of the previous bid that was overtaken for the new bid. Assume that it does that 42 times, and then close the bidding stage. It calls the close function, emits event 2, and then in turn calls the refund of the last losing bid, which then calls in cascade the refund of the remaining non-winning bids. The program trace for this execution is these 42 bid events followed by a close, and then 41 refund events. And the program traces for and the event traces for this program are defined by this context-free language. Even though in our example the events are constants, an event can be an expression which is first reduced to a value and then emitted as a side effect. And the operational semantics is defined in terms of pairs of program expressions and sequences that are observed during the evaluation. The property that we are interested in states that the stages of the auction occur in correct order, and the number of refunds are at most one less than the number of bids. Since we cannot express this with the finite automata, we use a symbolic automata with accumulator. Transitions in this automata are defined in terms of guards and updates of the accumulator. For this property, we use two accumulators, a bid counter and a refund counter. And the automata states that under the bid event, it self-loops to Q0 and increments the bid counter. Under the close event, transitions to Q1, where it self-loops under the refund event, incrementing the refund counter, provided that the relation between the bid counter and the refund counter holds. Otherwise, it transitions to the error state. Notice that the accepting state is the error state. Therefore, the property expressed by this automata is actually the complement of the language recognized by this automata. So we need to verify that the intersection with the event traces is empty. We can take the immediate approach and reduce this problem to a searching checking in product of the program and the automaton. And we can do that by encoding the automaton in the programming language, and then we perform a transformation on the program by passing the automaton configuration in and out of each expression, weaving it through the program, replace the EV expression by a call to a transition function, and finally we add the assertion on the final configuration. Then we can use the existing automated verifiers to verify this eventless program. However, they struggle. There are a couple of problems. First, weaving the automaton through the program increases the arity of the functions, and that impacts the performance of the underlying solvers for predicate synthesis. Then we have longer analysis because of the program blow-up. We have burden on the type system, and then also for verifiers that are based on refinement types, the lack of precise joins or the lack of disjunctive reasoning may lead to failure to verify because the transition relation is encoded as a sequence of if-then-else expressions. Another approach is via type and effect system. A proof is a valid derivation in the type and effect system. And in prior work, we have seen solutions where effects have been represented in terms of automata, omega regular expression, predicates in a fixed point logic, and other works have been focusing on algebraic characterization. In all these works, effects can capture both finite and infinite behavior, so they can reason about properties which go beyond safety. The great thing about is the compositional verification. The downside is that they're not fully automated. That leads me to introduce our work, which is a new method for scalable effect inference, which is grounded in abstract interpretation. In the next part of the talk, I'll introduce a novel abstraction of temporal effects, which are based on symbolic automata with accumulators. I'll show how we can embody these abstractions in the novel accumulative type and effect system that provides the proof, and I'll show our implementation and our evaluation results. Let's begin. The key idea is that in the concrete semantics, we can relate event prefixes with environment valuations. Let's see that by zeroing in on the bid event in our example. Before reducing the EV1 expression in the environment, we have several variables. Let's focus on the environment variable I. And the event trace prefix at this point is empty. After the bid event is emitted, event sequence now become 1. And notice that the number of occurrences of 1 in the event sequence is equal to the environment variable I. We can see better after the second bid is placed, and the same invariant holds after each bid event. Accordingly, we exploit this by modeling the concrete effects as sets of pairs of environment and variables. I'll walk you through the construction of our abstract domain for effect by using the bid event as example. The first observation is that we can represent the event trace prefixes by reachable configuration in the property automata. Effects in our first domain are exactly that, sets of pairs of reachable configuration and environment valuations. Next, observe that we can exploit the structure of the automaton, and we can partition this set by the control states. However, these partitions are infinite. That's untractable. So in the next step, we abstract these partitions by elements of a relational numerical domain, such as polyhedra, octagon, and so on. So for example, the mapping from Q0 to this set of relational constraints says that represents all the event trace prefixes that end in, whose run on the property automaton end in the control state Q0 with the accumulator value which is constrained by this set of constraints. And the other states are mapped to bottom, and that means that have not been reached. So our effect domain is the domain of these SAA abstractions. We have formalized the domain, as a composition of Galois connections defined for these domains. I'll skip over the technicalities. Please see our paper for the full details of our construction and the soundness proof. Next, I will show you how we can take this abstraction and embody in the accumulative type and effect system that provides the proof. For this typing judgment, on the right side, we have the typing context gamma and the effect context phi, which summarizes the prefix traces up to the evaluation of the expression E. The expression E dictates how the extension is being formed. Tau is the refinement type, and phi prime summarizes the extended trace prefixes with the evaluation of E. For example, this is the typing rule for a single event where an event value is appended to the trace prefix. And this is soundly abstracted by this effect extension operator, which we require to be defined in the effect domain. Let's build this intuition by looking at the inferred effects for our bid event. This typing judgment corresponds to the conclusion of the rule. In the context, the effect says that only Q0 has been reached and the bid accumulator is 1 less than the environment variable I, while the refund accumulator is 0, and then we have other relational constraints in the environment, and Q1 and Q0 has not been reached. Recall that under the bid event, the automaton transitions back to Q0 and increments the bid counter. So the extended effect reestablishes this invariant that the bid accumulator is equal to I. And on a side note, the refinement type for the EV1 expression is the refinement type for the unit val. Next, I'll talk about our implementation and evaluation results. We have implemented a prototype, EV drift, for OCaml programs extended with EV expressions. It builds on existing abstract interpretation inference of refinement types, and we have improved the precision of the analysis by adding support for trace partitioning. And we have shown that our method can verify a wide range of SA expressible properties, such as tracking disjoint branches of a program, resource analysis, verifying a reentrant lock, tracking bounds of a variable, amortized cost analysis for a two-list implementation of a queue, or also cost analysis for binomial heap, monotonicity, and others. And we asked the question, how did we do? How effective is EV drift compared with existing tools when they're applied on the reduction that I showed in the first part of the talk, where we transform the eventful or effectful program into an eventless program. Out of the 23 benchmarks, Drift managed to verify 12 with a geomean of 1.9. OCaml verified 6 with a geomean of 1.6. Mochi 11 with a geomean of 6.7. RETHFL 18 with a geomean of 5.1. While EV Drift managed to verify 21 with a geomean of 0.9. So in summary, we've introduced a first abstract interpretation-based approach to verify safety temporal properties, a novel effect abstract domain with increased support for disjunctive reasoning, that it's embodied in a novel cumulative type and effect system, and we have shown an effective implementation that can verify a wide range of SA expressible properties. Please see our artifact here. Thank you.
We have time for a question. If you'd like to ask a question, please come to the mic here. And identify yourself and your affiliation, please.
Hi. Thanks for the great talk. So I want to ask the question about the accumulative type and effect system. So it seems that the phi and phi prime are somehow specialized to the specific automaton. All right. So I'm wondering, you consider abstracting such a state of the automaton to reuse the verification result to other automaton or other setting?
Thank you for the question. It's a good question. I think one of the reason the accumulative type effect system is able to work is that the effect domain is actually not compositional. This is like a whole program analysis. Whether it works with other automata, I think it can work because as long as you maintain this whole program analysis constraint.